a todos.
Hola, hola.
Hola. Hola.
Sí. Ahora tenemos todo. Ah, no. Creo que tenemos dos fans. Vamos. ¿Quién es el otro? ¿Es Roy?
Profesor,
Sí.
cuando uno entra por Canvas, ¿solo ahí queda registrada la asistencia?
Creo que no. No nos importa en qué manera vas a entrar. Sí, creo que hay uno. Canvas va a grabar un reporte desde Zoom. Y Zoom está afuera del proceso.
Ok.
No me explico bien, pero entiendo. Yeah. Okay. Who else do we have? Who is the other? Con J.
Oh, me. Jenny.
Ah, Jenny. Okay, perfect. No,
Yeah, I don't know. I
So-
click
no, no,
in the link through
I think,
Canvas.
yeah. I think there's, I registered twice in Canvas and maybe that just completely screwed things up. No sé. You should be able to rename yourself. And if you go to participant list, there's an option to rename yourself.
Yeah, but I can change my
Okay.
image of profile. But
Okay. Yeah, I changed it for you. Okay. No, all good.
thank you.
Okay. Let's see. So where are we? Yeah. Also, the sessions are all recorded, and so you can go back and rewatch them as much as you want. I don't recommend it too much, but you can. Okay. So just to clarify a couple of things, right? So we moved the homework to Friday. I didn't want to get too far set back, but I wanted to give you a chance to see black body radiation, even though we're all familiar with it. The other one was, I think, Jenny, you had a question last time about alpha versus kappa. And in my mind, I was trying to make things, clarify things, because there's two different coefficients that come up, and one is the linear absorption coefficient, and then at some point they switch to just absorption coefficient. And I was trying to distinguish them, but kappa is also the mass absorption coefficient. And so, yeah, I think I screwed things up more than I made them simple. And so I've rebranded it all as alpha. And so I uploaded a new PDF. I can share my screen. So if you download the latest PDF, you will get so alpha, and then alpha equals kappa here, and everything here is now alpha. Right, so hopefully at least it will be a little bit more straightforward. I think I caught all of those. We will have to make the distinction further along about linear versus total, which is also a little bit confusing. Okay, hopefully that solved that issue. Yeah, I also relabeled all of the lectures. So lecture 0, which was the first one, I actually relabeled it as 1A. And then this lecture I labeled as 1B. And then this lecture that we're going to do now is 1C. It's transparent. When you click on the link, it'll just download the new file, but the file will be slightly changed in the PDF. Okay, so without further ado, let me find the right one here. It should be this one. And we can start. Are there any questions about the past lecture? Any issues you want to bring up before we start? Oh, no. Okay. then let's move on to black body radiation. And here, I think this is, again, I'll fairly much review, but one of the most important and ubiquitous sources of radiation is black body radiation. And at least from a theoretical standpoint, the intensity and the spectrum of a black body radiator should only depend on the temperature of the black body or on the cavity that is creating the black body. And of course, we have a couple of different derivations depending on what wavelength we're in. And so we have the Rayleigh-Jeans law, which is the power loss slope at low frequencies. And then we have the Planck radiation law, which is encapsulating all wavelengths. And so because it's so fundamental, it's worth repeating here and kind of at least doing a very simplified sort of theoretical exposition of it. So we can start by just considering we have some cavity, and the length of this cavity is much longer than the wavelength. And so you have many wavelengths traversing this cavity. And so this cavity is filled with some radiation, which is in thermodynamic equilibrium. And this cavity confines the radiation for at least a long enough time where it becomes into equilibrium. The cavity and the radiation come into equilibrium, right? So we've kind of come into the situation after it's already come into equilibrium, which takes some time. And so the walls of this cavity confine the radiation. We assume they have some non-zero conductivity. If the walls had zero conductivity, they'd be transparent. And they would generate no currents here in response to the electric field, and the radiation would pass through unaffected. So we have some wall with some non-zero conductivity. The equilibrium field strength here at the walls should be zero. And so modes where the electric field isn't zero would be called lossy walls. In other words, that you would tend to lose some energy through it. And so what this means by imposing this condition is that you can only have standing waves that end up having E equals 0 at the wall. And so this sets up some situation where you can only have certain wavelengths that satisfy that condition, right? And so basically only standing waves with E equals 0 at the walls will persist after some time, which is a lot longer than the crossing time of this radiation. So this is the sort of situation we've pictured, at least in one dimension, right? So you have radiation here, and you can only have the radiation which has starts at 0, ends at 0, with some length Lx. And so we can then define which waves will actually exist in this scenario, and generally we'll have standing waves that will have the wavelength divided by 2 times n, where n is the number of wavelengths that can be encapsulated between L. And so n could be 1, 2, 3, et cetera, et cetera. Right. Okay, so this is kind of one-dimensional basic scenario for this black body radiator. And so we have these boundary conditions, and so we have the discrete wavelengths that exist there. We can define these. Similarly, we can expand this to multiple dimensions. So instead of just X dimension, we can go to Y and to Z. And so we have something similar here. And once we define multiple dimensions, we can also have waves that go diagonally, right? They're not just in one dimension, but they're in 2. And therefore you can then allow or house more possible wavelengths, right? Because these angles allow you to have many, many more possibilities. And so you can define a wavelength as being a sort of fractionally in X, and that fraction is related to the cosine alpha. So a wave is propagating in this direction. It will have a portion which is in X and a portion which is in Y. And so we can set up a situation where we can define this wavelength in terms of its principal components. in the XYZ axes. And of course, generally speaking, let's see, so the wavelength here is measured in the direction wave normal. And so let's see, is that correct? I think this should be the opposite sense here. Let's see. Oh, no, okay. So this is, let's see. So this would be that, and this would be smaller than 1. Okay, yeah. So in this sense, this should hold. Okay. So we can define these for different angles. We have these 3 different angles, and we then can set up boundary conditions. So we have sort of the fractional number of nodes in the x direction, the number of nodes in the y direction, the number of nodes in the z direction. And so we can define these, we can plug in our values of this using these formula, and we can arrive at something which is relating the wavelength to the length of the cavity in one direction and this angle, which is propagating. And if we sum all of these, we square this, we sum the squares of these things, we get the square of this, and then we get this. And this thing, by Pythagoras' theorem, is 1. And so we have a situation where this applies. And so generally we can say that the wavelength of the frequency depends on the length of the cavity, which is now generic. So we've encapsulated the length into this L and these components, which are all positive integers. Okay. So this gives us some sort of grid. We have a length L here, which is the size of our cavity. And we can think about this as having some sort of width or a shell of size, which is dp. And so generally speaking, this sort of grid of points here will allow certain standing waves to exist, right, in this sort of lattice structure. And so each point here represents a possible mode of electromagnetic radiation. And so the space density of these points in this lattice ends up being unity. And the number of points in any sort of volume is equal to this volume. So this sort of situation, we can define this radial coordinate rho. And so this coordinate, the square of this coordinate is equal to these guys here. We can redefine this frequency as a function of this sort of radial coordinate, the length, and c, and divided by 2. And so we now want to know the number of possible modes that exist in some very small frequency range. And so we can set up number as a function of frequency over this small frequency range. And we want to look at the sort of volume within a very tiny sort of radial shell, right? So between rho and rho d rho. And we multiply this by 2 because we have 2 different polarizations of the light. And so the total number here will just be the shell, right? So the surface area of the shell is just 4 pi rho squared, and then the thickness is d rho. And then we end up having a factor of 2 for each of these dimensions, but then we multiply by 2 for the polarizations. And so plugging in our sort of moving all these variables over and substituting for rho, we end up here having sort of the rho squared portion here. The 4, the 8, and the 2 all disappear. And then we have, for d rho, we have this. So we just take the derivative with respect to mu here. And so this gives us a total number. And so we can then think about this, not necessarily in terms of number, but we can think about it in terms of the average energy that exists within this sphere. And so if this is in thermodynamic equilibrium, we can consider the energy equal to KT, the average temperature here. And this just follows from our sort of standard Boltzmann law. This doesn't really apply for quantum mechanics, but we'll get to that in a little bit. And so if we assume that the average energy here is KT, and this is the average energy per mode, then we can calculate our spectral energy density, right, which is the energy per some volume. And so this is going to be the number of possible modes that we have, the average energy, KT, and the volume, which we'll take as just L cubed for the moment. So some cube. And so again, plugging in what we had previously here, we can arrive at something which looks like this. And we can, of course, what's interesting is that the volume drops out. And so it doesn't really depend on the volume. And what it depends on, the average energy, and just depends on our average energy of the system, KT, a factor of 8 pi here, and then the frequency dependence, which goes as frequency squared. And you'll notice that this thing looks somewhat familiar. Right? This is starting to look like all the variables for the Rayleigh-Jeans law.
Sorry, I have
Yeah.
a question here in this equation.
Sure.
Because I don't know if the number of
Modes.
this number of modes, sorry, should have to this delta nu, because I mean n nu the nu in the previous equation remains
was for a shell.
Yes.
Yeah. So basically what we have here is this shell thing.
Mm-hmm.
And
if we replace this value of n nu the nu, this the nu should survive in the equation. I don't know if I explain myself.
Yeah, no, you explained it perfectly fine. So so this thing ends up being slightly different. So this n nu is the total number. So you kind of have integrated it up again. But then the energy density that we're taking is in a small range of d nu. So we could think about this d nu as being on this side. And so what Rubicki and Lightman did was just move it back over here and say, okay, we have this, which is basically this, and we're just going to substitute in this thing here for NV and not touch necessarily the d nu, if that makes sense. So it's a little bit of hand waving magic. I agree. Yeah. But that's in essence the idea was that they would oops, let's see, wrong way. Yeah, basically you had this thing. So in theory, this thing doesn't leave yet, and they have to integrate over it. And so here, generally speaking, this has gone away, and this is the trick. So what's happened is we have integrated over this volume here at that point. Okay. So we can also think about this thing as what we defined previously, which was the specific intensity over some solid angle. And so we can relate these two, and we do that, and we can plug this in as being the sort of black body radiation, because that's the special case we have. And so we have that this thing is equal to this, and so we can define a black body radiation, which ends up just looking like a subset of these parameters. And this, of course, is a sort of hand wavy way of deriving the Rayleigh-Jeans law. Now, it didn't take into account any quantum mechanics. And therein lies the problem, because it only is valid in a regime where the frequencies are much, much lower than the average energy that we're talking about of the system. And so in order to get a more realistic term, we have to actually move to quantum mechanics. But the idea behind this is the same, is that what you want to do is count the number of possible photons that might exist within this volume, and then use that to derive this. And so Rubik and Lightman go through this whole derivation again, but now in sort of a quantum mechanical sense. Before we get there, just a note here, here the brightness is proportional to the frequency squared. And this is because the volume here is a spherical shell in 3 dimensions. Part of the reason why we keep the shell, just to come back to Laura's question, is that this system ends up being optically thick. And so the radiation that we see ends up coming from the outer surface. And so this is kind of why we keep this shell rather than integrate it through the entire volume. Does that make sense, Laura? You can just nod your head. Okay. Right. So this is why it ends up retaining the shell structure. But this is, of course, in 3 dimensions of the shell. So it's the total radiated energy, or not energy, total radiated specific brightness. Okay, so this is proportional to this frequency squared. We're assuming all modes have this energy KT. This is a very classical assumption which breaks down a high frequency, as I mentioned. If you go to high nu, you get what is called the ultraviolet catastrophe, right? And so this thing no longer holds, and you would estimate for a given frequency and temperature, you would estimate way too much intensity versus what you actually get. Okay, and then this other thing is that, of course, it's independent of direction. It's isotropic, which is one of the input assumptions. Okay, so coming back to this sort of idea, the flaw in this derivation was this classical assumption that basically the radiation modes all had this energy E. And so if we think about a continuous distribution based on a Boltzmann probability distribution, this probability as a function of energy is going to go as the exponent of E divided by KT. And so this extra sort of functionality, which in essence is the Wien drop-off, factoring that in, then you come out with something which ends up looking like the Rayleigh-Jeans law on one side and the Wien law on the other side. So this particular assumption of assuming a Boltzmann probability, that if you have some energy E, it's really easy to have energies lower than that. It's not so easy to have energies higher than that. And so this implies an average mode, or an average energy per mode, which looks like this now. So again, it's still KT, but now what we have here is that the energy multiplied by this probability function, if you integrate over it, and then divide by the probability function, the average energy is still KT, but at high energies, this thing has a cutoff. So this is how Planck postulated this. And so he basically said that we have a bunch of mode energies that are not continuously distributed, but they're quantized, which is, again, similar to what we were talking about with the modes having to be quantized within this black body structure. And the energies here are just related to the mode and h nu. And so now here, again, n is any number you want. And this h is now Planck's constant. Right. Okay, so this probability of energy, which we can now substitute in nh nu, and so then plugging that in here, we have the exponent of minus nh nu divided by kt. And so then the average energy plugging this in again looks like this. We multiply by the energy and this thing, and then over the probability. And so if we evaluate these things, so this thing is just this exponent, so we plug that in here, we have the exponent here, and if we evaluate this, this average energy ends up equaling h nu divided by this exponent, where we've now gotten rid of the n and gotten rid of the minus 1 here. So that's now the average energy as opposed to just kT, or rather this is equivalent. So given that we have this, this is, a photon of a frequency nu. And so we can now go back and calculate the average number of photons. And this is also known as the occupation number. And so the average number of photons is just the denominator of this previous thing. So we have, this is the energy kT, and this is the number of photons. And so if we then correct this law now, what we end up having is the classical sort of formalism here, but then we have this extra portion, which is, now this is just averaged out. So this is h nu, but then divided by kT to kind of make it all normalized, and then the number. And so this thing, right, this is just the Rayleigh-Jeans portion of it, and this is the quantum mechanical extra factor, the correction factor that we need. And of course, this has this nice behavior that it cuts off at high energies. And at low energies, this thing goes to 1, and you end up with something which looks like this. So reconfiguring this, we can cutting off all of the extraneous parameters, we get something that looks like this, which is our classical Planck law. Okay, any questions?
Yes, I have a question. From which formula did we derive this radiation law? Yes, that is the question.
Well, we derived it from a sort of hand-wavy sort of mechanism where we started with back here of setting up a situation where we have classical sort of nodes that can exist given this. So we had some thought experiment where we said, okay, we have some system and it can only, after some time, once it's equilibrium, house certain waves, right? So the interior of this is quantized at some level. And all of the things that have wavelengths or frequencies outside of that end up eventually leaking out during this process of equilibrium. So that thought experiment, right? If we just then go through and try and quantify, okay, what is the average energy of the photons here? What is the average number of photons here? We end up with something which is a classical derivation. And then we try and correct for that classical versus quantum mechanical approach by just applying a correction factor. And the correction factor is simply based on the fact that you apply a Boltzmann probability distribution. And the functional form of the Boltzmann probability distribution is that it has a distribution which is one-sided to some extent. So, or if you think of it in linear terms, it's not one-sided, but you have energy and you have, let's say, plus or minus that energy. And then when you think about it in logarithmic terms, what that really means is that on one side, you have between the energy and 0, which is a huge, huge range, logarithmically speaking. And then, energy plus energy is just a factor of 2, which logarithmically speaking is very tiny portion, right? And so that distribution ends up being kind of one-sided, where you have lots of possibilities here and very little, some value above the energy. And so just applying that portion of it, and then just doing a sum through the possible so all we're doing is evaluating this integral or evaluating the sum of these quantized bits, right? So once we know that this integral is quantized, then we can write a summation rather than an integral. And in doing this, if you were to evaluate this all out, you end up getting this result. This is about 3 pages of math, which I'm not going to go into. It's done in detail in various places. You can look it up. Did that answer your question? Hopefully.
I have another question.
Yeah.
In the next slide. In the Planck's law, the factor h nu over kt, it's normally it's related with the normalization of that equation.
Well, you need what you need here. This is energy and this is energy. So you end up with something which doesn't have any units, which you need here. So it's merely a way of relating the photon energy to the average energy of the system.
Okay.
And it comes back in here from this thing.
Okay.
So imposing this condition, you end up with, and evaluating this for all of the different values of n, and all the different values of n, what you end up with is, this thing pops out, and the n's drop out, but you end up with this exponent, which is related to these values.
Okay. Thank you.
And this ends up being, when you evaluate this very high frequency, this thing becomes important, and you end up with the Wien law. Okay. Let's see if there's no more questions. And so if we were to integrate this thing, right, going from 0 to infinity, we end up with something which is now not infinity, as it was if you took the Rayleigh-Jeans law, but integrating this up, we end up with a factor of temperature to the 4th power and an extra factor, which is a bunch of constants. And so this extra factor here is just all of these constants. And this is known as the Stefan-Boltzmann constant. Right? But it's just combining all of the different gory constants into one. And it has units to kind of normalize this between temperature to the 4th power. And it has, again, remember the steradian here, because it's got the solid angle, because this is an intensity or a surface brightness, but it relates these two. And there's this extra factor of pi. And so what, of course, is interesting, remember that at the surface of a black body, you end up having that the flux is equal to pi times the black body. Right? So pi times the specific intensity. If you move pi over here, this ends up being flux. And so the flux at the surface of a star, for instance, or any black body, is Stefan-Boltzmann constant times temperature to the 4th power. That isn't the flux generally, right? It's the flux at a very specific place, which happens to also, you can then easily convert it to the luminosity. Okay. Whenever you look up the Stefan-Boltzmann constant, sometimes you never see a steradian, and so you have to be very careful. So it can be a little bit confusing. If we're in the, so we had the Rayleigh-Jeans limit. If h nu is much, much greater than kt, then we have the Wien law, and the Wien law looks like this. So it's just the exponential, very strong cutoff as you go to higher frequency. So as this becomes large, this is negative, and so an exponential negative becomes 0. And so you have the fall off, even though this is going up as nu to the 3rd. This ends up being stronger than this. Okay. So what this looks like when you put it all together, this is I like this figure, even though there's a lot packed in here. So you have frequency, you have wavelength here, and vice versa. Then you have the surface brightness here. And so what you can see is if you have different temperatures, right, going from 1K all the way up to 10 to the 8K, you see that and this is for an object of the same radius, right? So you're just heating up the same object for different temperatures. And what you notice is that the peak moves, right, in this direction, but also the total intensity, the total surface brightness also gets higher. And so you get a movement this way and you get a movement this way. And that's important to remember. Here's the Rayleigh-Jeans portion, here's the Wien portion, and of course the peak is related to the temperature, which we'll come to in a second. Okay, so we can again go and calculate the specific energy density or spectral energy density. The spectral energy density is related to the intensity, which in our case for a black body is related to the Planck law. And so integrating this between 0 and infinity, right, we end up with a total energy, basically a radiation energy density, which is sort of the bolometric energy density, which is related to the Stefan Boltzmann constant times T therefore. And that'll give you the total, amount of energy that's sort of radiated away in some volume. And again, this volume is at the radius of the star. So we can also consider a frequency max, and I think I didn't change the fonts here, which is annoying me because I started to change all of them, but I missed this page. Okay, there we go. And let's see. Screw this up a bit. Okay. All right, so now that looks a little bit more like frequency. Right, so if we look at the max frequency, or the frequency at which this thing is a maximum, so we can look for the derivative of our black body frequency dependence versus frequency, where that equals 0, and that's going to be the top. So if we take that derivative, we end up with a maximum frequency, which is about 59 gigahertz times the temperature. So the frequency and the temperature are linearly related. Now, Vmax isn't quite the same as C divided by lambda max. And this is because B nu is different from B lambda, right? And so factoring that in, lambda max will end up being slightly different, but this is the formula for lambda max. And this is, of course, known as the Wien displacement law. And it looks like I cut off something there. Let me get that back. There we go. Okay, and you'll see this quoted by different people. So optical astronomers often might measure lambdas instead of nus for whatever reason, historical reasons. But this, of course, is why you have this displacement. So a factor of 10 in temperature is a factor of 10 in frequency. Right? But it doesn't necessarily go a factor of 10. Let's say, well, each of these is one factor of 10. So it almost goes about a factor of 10 here too, as well. Okay. So that's black body radiation. And so we can also recall that this thing is directly proportional to temperature. In the Rayleigh-Jeans portion of it. And radio astronomers in particular, because they often worked in the Rayleigh-Jeans regime, they would use this formula quite a bit. And in actual fact, they would turn it around. And what radio astronomers typically measure is a voltage, which they can turn into a temperature. And so they actually found it convenient to work in terms of temperatures. When they talk about a source, they talk about it in terms of a brightness temperature. And basically what they're talking about is a spectral brightness, I knew, which is the equivalent of a black body brightness temperature, TB. So they're using this formula, but when they're quoting a brightness temperature, they're really quoting an intensity, a spectral brightness. And so it looks like this. And the point is that they would quote this regardless or irregardless of whether the source was actually intrinsically a black body or not. And what's sort of interesting about this, so if you turn this around and you measure the temperature as a function of frequency, you should get this back if it's following a black body. If it's not following a black body, this thing is going to be more intense than the black body, and you measure a temperature which is higher than the black body. And this has some interesting consequences. So if you, for instance, are measuring a source that is strongly beamed, and you can measure the size of the source, so you have a certain amount of radiation coming from a certain sized source, that temperature, you can relate, if it was a black body, would have a certain temperature. And then you can look at the brightness temperature and you can say, oh, well, this actually has a brightness temperature of 10 to the 10 Kelvin. And there's no physical thing that we know of that, for this size that can have this temperature. And so they can use that as an argument to say something is non-thermal versus something that's thermal, meaning the origin of the photons is thermal, black body, or the origin of photons is non-thermal, aka synchrotron beaming, for instance, or inverse Compton radiation, or what have you. You'll see this is sort of common within the radio astronomy community. All right, and the important thing here is to note that not to confuse brightness temperature with physical brightness. That's the key thing. And so just to give you another example here, so they should be equal for an opaque source, so some source that has tau much greater than 1. But the brightness temperature of a semi-transparent thermal source, such as the Earth's atmosphere, is going to always be less than the kinetic temperature, which is also another possible scenario to consider. And then the one I was talking about is non-thermal sources can have very, very high brightness temperatures. So pulsars, for instance, actually have brightness temperatures of 10 to the 26 Kelvin, which is very ridiculous. And of course, this allows people to determine that these things are non-thermal, beamed, unbeamed, etc. Okay. So any questions before we move on? Okay. So
I have a question. I'm sorry, I didn't find my unmute.
yeah.
What are we referring with non-thermal or thermal sources?
When we talk about a thermal source, we're talking about a black body radiator.
Okay.
Right. When we talk about non-thermal sources, in general, we're talking about things that are not,
Black body.
which is most everything else. There's a slight exception when you talk about Bremsstrahlung, which is technically it's thermal, but it's a plasma, and so it kind of is in between. But it also behaves a lot like a black body, so which we'll see in a little bit. Well,
Thanks.
In chapter 5. Okay. All right, so one other thing to kind of consider is when we think about radiation transfer, we're thinking again, I had mentioned, giving you an example of Kirchhoff's law before about the sort of cavities coming into equilibrium between the temperature of the cavity and the radiation it's sitting in. And so we can use Kirchhoff's law to again evaluate this. And so it's useful to kind of think about this. So a generalized version of Kirchhoff's law here, we have an emission coefficient and an absorption coefficient. And if we know one of them, we can use that information to calculate the other one, and vice versa. And so the issue we have is that while Kirchhoff's law is fairly generalized, it is not always intuitive. And this is because our eyes only see a certain wavelength range. And so we don't necessarily have Kirchhoff's law ingrained visually, so the human, as it evolved over time, it can't see how, an object which is at room temperature, so it has a 300 Kelvin emission, we don't see the light that's coming from that. And so we're not able to be able to understand that, okay, this object is absorbing sunlight, which has, is emitted from something else, but it's absorbing it, and then it's re-radiating that as something else once it comes into equilibrium with that radiation. And so we don't have that concept ingrained because of our limited range of the visual wavelengths. And so, we also could have like a glass of water where most of the light passed through it, but some of it stayed in there and was able to heat the water up. And so what we could do is say, okay, well, we measure the light before it goes in, we measure it after, we see that there's a 10% difference, and we notice that the water has heated up over some period of time, right? So we can do those experiments and kind of understand that there is some radiation transfer going on. One slightly more practical example is Kirchhoff's law when we think about charcoal fire and we have flames. And so we can see that an object is being heated up and starts to glow because the temperature now is a few thousand Kelvin and the emission is actually in the visible wavelength range, right? So we can see this happening, and it's a little bit more intuitive. So Kirchhoff's law here is always very significant in IR radio wavelengths. And this is because h nu divided by kt is always less than 1 for most purposes here, at least with things that we have on Earth locally, the temperature on the surface and so forth. So we can now consider this sort of more generally. We have emission, we have absorption, and a third component, which we hadn't talked about before, is reflection, right? So those are the three objects. We have an object which is opaque and radiation is imparted on it. And some of that radiation might be reflected away as a function of wavelength. Some of it might be absorbed as a function of wavelength. And then some, because it's heated up for that radiation that's absorbed, it will emit. And so there's a balance of all these things. Typically, the absorption and the reflection get added up into a sort of more generic sort of term. But you can kind of consider them, if you have a photon, you have some probability that it will be absorbed, the absorption coefficient, and you have some probability that it will be reflected, the reflection coefficient. And these are functions of frequency. And so obviously the total amount of radiation should be constant, and so this plus this should equal 1 for the radiation that is incident on an object. Okay, so the emission and absorption coefficients of an opaque body in local thermodynamic equilibrium are not independent here. And they're related by another form of Kirchhoff's law, which is that the amount, basically the energy absorbed and the amount of energy emitted when it's in equilibrium should more or less be the same. And so we can come back to our mental construct here. And here we have an opaque body, and it's surrounded by this filter, which passes light of a certain frequency, but nothing else. So no no atmospheric transformation, no particles are moving across this filter. It's just light. And basically this cavity, this thing has a temperature. And if you let light pass along for a long enough time, eventually this outer shell will come into equilibrium with the inner shell. And so in equilibrium, we can calculate a spectral power that's absorbed per unit area. And this spectral power absorbed per unit area must be equal to the power emitted per unit area in order to have balance. And so we can calculate this spectral power absorbed. It's just the probability of the absorption. And then we have the black body radiation and an integral over the solid angle. And so we can integrate this over both theta and phi and over the entire sphere. And so we can get something which is absorbed, and we end up with at the surface of this source, which is a sphere, we get this, right? And this is just times the absorption coefficient. And likewise, we can calculate the emission. And so the spectral emissivity is just the probability of being emitted times that. And the fact that these have to be equal because of energy balance and equilibrium, this means that this thing and this thing, and this should be an alpha, not a weird thing. Okay. This should equal this. And then of course we have another formula which is related to the reflection. And so the reflection comes in here as 1 minus R. And that's the probability of it being reflected. And this is just another form of Kirchhoff's law. And so we can think about this in terms of a brightness temperature, for instance. And so this brightness temperature will be related to the absorption probability times the actual temperature, or the 1 minus the reflection coefficient times the temperature. And so if you have a perfect absorber, this ends up being 1, and the brightness temperature equal to the temperature, at least in the low energy regime. And if we have a perfect reflector, then basically this brightness temperature will be 0. And you'll just have all the light is reflected. Okay, just some basic laws. And so what this ends up allowing us to do is so we had the absorption coefficient and the emission coefficient, which we defined from last lecture. And so we can add an extra component, which is the scattering component, right, or the reflectivity. And so this is a very common process. And so we can factor it in as follows. And so we can deal with sort of individual scattering processes on a microscopic level later on, but on a macroscopic level, when we want to look at how this affects light, we can factor it in as follows. So here we're going to assume that this is a coherent isotropic scattering, meaning it's elastic, it's monochromatic, and so it won't always hold, but for the moment it makes things simple to sort of calculate. And so we have the intensity, which is as a function of solid angle, and if it's isotropic, right, then there's no relation based on solid angle, or no deviation based on solid angle. So it's just that, which is equal to the mean intensity. And so scattering is a more generic form of reflection. And so we can adopt the past formalism here. So we have the absorbed and emitted powers, which are equal. And we can then define the emission coefficient as the scattering coefficient times the radiation that's already there. And so this is a form of the emission coefficient, right, which is related to scattering. There's another form, which is the absorption and re-emission. right, which might be a black body or some other process. And they're both components of the overall spectral emissivity. So we can think of this scattering component when it's pure scattering. And so the absorption coefficient of the scattering process is just this. Then what we end up having is a transfer function where we have the change in the intensity is related to the intensity times the scattering. So this is the amount of light that was originally there that's scattered out of the line of sight, right? That's why it's a negative. So it's decreasing. And then we have this one, and the two negatives cancel. And this is the amount of radiation that's scattered in all directions. And so this can be, sort of considered a source function to some extent, but it's really dependent on this. So putting that all together into a more complex process, we might have emission and absorption, and they could be controlled by various processes. And so we have some incident radiation, and it's moving through a medium, which will absorb some fraction of it, right? And it will re-radiate that as some black body. And we have another process which scatters some emission and scatters it isotropically as this. And so plugging that all together, we have this lovely thing, and we can move some of the components back, rearrange these things. And so this is equal in both of these. This is not necessarily equal in both of these things. And so we can define something called the source function, which is this fractional quantity. And so this hides a lot of the complexity of what the processes are, but it sort of simplifies this into the original intensity and some source function, which is complex. And it's related to our absorption coefficient and our scattering coefficients, or probabilities, along the line of sight. We can also define what we call a net absorption coefficient. And this is where I was trying to break, now you can see what I was trying to do was separate out these constants so that they weren't too confusing. Often this thing here is sort of rebranded as the extinction coefficient. And that's to distinguish it from alpha. But sometimes it ends up coming in as alpha, and sometimes it doesn't. So if we have a medium which is in thermodynamic equilibrium, this thing is equal to the black body. This thing, so this is now a black body, and so you can remove that. You have an alpha plus sigma, and alpha plus sigma, they divide out, right? And so you just end up with this thing equals the black body. And if the medium is isolated, then you don't have any scattered radiation, and you just have this. But you have to recognize that you still have this component here, because this medium will emit, but also scatter some of the radiation that it emitted. Right? And so that's why you keep this here. Okay. So how are we doing in time? Oh, not too bad. Right, so this is the sort of most generic form, and we could use this to, plug in various emission processes here and here. And this will give us a way of being able to calculate everything. Okay, now a couple of specific examples which are sort of useful to think about. We had talked about this random walk process. I had mentioned it before, and now let's examine it much more closely. So let me get some water. So we have this scattering process, and if we also have an absorption process and we have a scattering process. And so I talked about the absorption process before. So if you have tau greater than 1, you absorb the photon, right? And then sometime later you might emit it again. via backbody or via atomic line emission, whatever. And then it might travel a little bit of distance and be absorbed again, and so forth. And that process was the random walk. In the same way that you can have absorption, you can also have scattering, right? You can have an electron and a photon interact, and you can have Thomson or Compton scattering. And so it's sort of generic. So we can think about this random walk process in terms of the average photon moving through some material that has an optical depth tau. And basically the probability of this photon traveling at least one optical depth is related by this here, the exponent of minus tau nu. And this is the probability that it will be scattered. If this process is isotropic, then there'll be an equal probability of scattering in all directions. Right? So it might look something like this here. And we can consider a couple of different quantities. One quantity is the distance between the emission and the scatter, or the time it takes for the photon to be scattered, right? Because this thing is random, after every process, you'll end up with a distance at the end, which will be the net displacement. So this net displacement R is just the sum of the successive vector displacements, right? So it's just this. And so in this particular situation, right, the net displacement might be this, or it might be this. So it's just the sum of this. So we can also take the average, and we can talk about the average distance traveled. And the average distance traveled is all of this, right? And so the average of R is always, you know, it should always end up being 0 here, but the actual distance will be potentially quite large if it's purely isotropic and the medium is infinite. So what we need to actually do here is take the root mean square of this value to get an actual value, which is how far this photon has actually traveled. And so if we take the mean of the square, right, this is equal to this distance traveled, and this is just equal to the sum of this times the cross products of that, et cetera, et cetera. Now for isotropic scattering, the dot product terms should vanish, and we end up with something that looks like this. So this net displacement is equal to n, where n is the number of scatters, times the distance of each photon before it was scattered. Right? And so it should look something like this. Just the square root of n. So this net displaces gives us an insight on the mean number of scatterings, right? At least for some finite medium. And so if we have a region where we have a large optical depth, then the mean number of scatterings will end up being set by the size of the region. Right? So once L, which is the total distance, becomes equivalent to big L, that should be the mean number of scatterings before the photon leaves the medium. And so setting this thing to L, actually this is setting the net displacement to L, we can calculate it what n will be. And so n is proportional roughly to big L squared divided by little l squared. And little l is the path, the mean, what we call the mean free path, which is how long it takes for the photon to be scattered once. And so this thing, L divided by L, is just tau, roughly. And so n is approximately tau squared, when tau is much, much greater than 1. And you have many scatterings. For regions that are what we would call optically thin, they have a low optical depth, so tau is much less than 1. Then the mean number of scatterings here is going to be set by this probability here, 1 minus the exponent of minus tau. And this, when we expand it out as a Taylor expansion, is just tau. And so for low optical depth, the number of scatterings is just tau, not tau squared. And so when we don't know the thickness of things, a useful formula to adopt is that n is equivalent to this. And why is that? Why does this work? Anyone?
Sorry, I get lost a little bit at the beginning. I mean, the final parts when we are talking about the different optical depths, I understood very well, but at the beginning, no, I mean, when we, yes, at the beginning of this slide, yes.
Yeah, okay, so well, this thing is the net displacement, right?
Yeah.
And once the net displacement becomes equal to the size of a finite region, the photon escapes. There's no more scattering, right? So if we set this thing or this thing to L, right? Then this thing is the mean free path. That's just the length of each individual photon before it scatters, right? The travel path. So then, okay, moving this on the other side, we have big L divided by L is equal to square root n. Or rather, the L squared divided by little l squared is equal to n. Now, another thing that you have here is that this generally L divided by little l is going to be approximately equal to tau. Right? So that's what I was saying here. And the reason this is, if you have tau is roughly equal to 1, that means you will have one scattering over the median. And so, that more or less is fine. If you have, this thing is very small compared to this, then the optical depth is very high. You have many, many scatterings. That's all it was. And so this formula here is just a simple way of combining these two extremes, which are just, these are two regimes where you have, it's much, much greater than 1 or much, much less than 1. And so you have these two scenarios which look very different in terms of how the number of scatterings relates to tau. And if you merge those two, you can kind of get away with something which looks like this. At very, very large tau, this one dominates. At very, very low tau, this one dominates. And so, this is kind of a way of moving in between, especially if you don't know the optical thickness necessarily. And so you can integrate over this thing, and it'll disappear in one way or the other, one of these terms. That's all. Okay. Any other questions? This will come in handy later. Okay, so we can formalize this a little bit and talk about the mean free path now is really just, the probability of an absorption or a scattering. And so this distance here is proportional to 1 over this absorption coefficient and this scattering coefficient, which have units of 1 over meter or 1 over distance. And so this probability of this free path will end in absorption event or a scattering event, will then be these things. And so if this thing is an absorption event, we have the emission is proportional to this absorption divided by this factor here. And then if it's a scattering event, it's just 1 minus this. And so this would end up being the scatter. And this thing is now a little bit confusing because this is not the emissivity, but it's the true absorption probability. Yeah, exactly. And so this thing is often referred to as a single scattering albedo as well. And so it relates the reflectivity to the absorption. And so this source function can end up looking like this thing, where you now have the source function equals 1 minus this emissivity, but it's also the true absorption probability, times your isotropic emission, your isotropic scattered light. And then you have the actual emission that comes from a black body. And this is just, this black body here is just a marker. You could have another process here as well. But the idea is you have some emission of this related to the absorption. And in general, every process that is an emission process has an equivalent absorption process. And so, for a black body, it's this, but we could plug in something else at some point in the future as well. Okay. So we can then go back to this net displacement, and we can think about the mean number of scatterings using these new coefficients. And so let's say that we have an infinite homogeneous medium, it's in thermodynamic equilibrium, and we start a photon out. So the random walk starts, and from a thermal process, it's emitted and it ends after some n scatterings with an absorption event. Right, so you have photons emitted, scatter, 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 absorption. And of course, if the absorption process is a strong process, maybe you don't have any scatterings. So the total walk that this photon has before it is eventually absorbed again, this probability is based on the final absorption. And so the mean number of free paths here, n, is proportional to this thing. Remember that emissivity and absorption are interlinked when the thing is in thermodynamic equilibrium. So our net displacement is related to our individual random walks divided by this thing, which is related to n now. And so taking the square root of this, we have our net displacement is equal to the individual displacement divided by square root of this, and we can plug in our factor here, which comes from this. And so we have, it's related to the absorption times this thing here, so the half power. This net displacement has many different names depending on the scenario that you're trying to think about. It can be called the thermalization length because at the point where something's absorbed, this is the length at which a source becomes thermalized, where you get equilibrium. It can also be called the diffusion length, which is how long something takes to diffuse out, long in terms of space. So how much length is needed for a photon to diffuse out of a certain medium. Or sometimes it's called just the effective mean path. Note here that this thing, because this is frequency dependent, this is frequency dependent. Okay. And in fact, this also ends up being frequency dependent. So if we have a finite medium here, then we have a relation where tau is roughly proportional to big L divided by little l. And so we can define an effective optical depth. And the effective optical depth is equal to the absorption component times the absorption component plus the scattering component of tau. And here the individual taus here are the absorption tau is related to our absorption coefficient as a function of frequency times L, and our scattering tau is equal to the scattering coefficient times L, or L is the size of the region. Okay, hopefully this is clear. These are mostly just definitions. So if we have something that is optically thin, then most of the photons escape, right, without an absorption. They could still potentially be scattered a little bit, but if we have that case, so we have, let's say we have monochromatic luminosity per unit frequency, and this is given by a total radiation created in the medium. And so we have some amount of luminosity. This is the energy density times the volume times the escape time, just how long it needs to escape. And if this thing is optically thin, and this was just generated by a thermal process, then you have the, basically the energy density here is related to these things, and you have this escape time, which comes into play. If this thing is optically thick, then what you end up measuring here is simply that you're going to have a photon emitted, it'll be absorbed, re-emitted, etc. And most of the photons at the edge will be the ones that escape, and that's it. And so here we basically have a large number of absorptions before there's a final escape. And what this means is the radiation is in thermodynamic equilibrium, and that L star here would be considered the thermalization length, basically over the distance over which the TE ends up being established, right? With the link being the photons. And so here you would, again, you have a monochromatic luminosity per unit frequency, and you have an emitting surface volume, for instance, of the medium times the effective path length. And so here we have an area, we have a path length, and we have the specific intensity, Planck specific intensity, and this absorption. And so in this case, what you end up having is, roughly speaking, that this thing goes as this, the square root of this. Remember, this is proportional here, where are we, to this thing. Right. And so I think, let's see. Yeah, I think there should be an L here, if I'm not mistaken, to keep the units correct. Because this comes from this. But then, oh, we can relate this to tau. I think there's something hidden here. I think I need to think about it a little bit. At any rate, the point of this here is that if we don't have any scattering, just an absorption process, what this ends up being very similar to, this thing will go to 1, and so this disappears. And what we're left with here is something pretty close to the Planck law. Or not pretty close to the Planck law, pretty close to a sort of classical black body. And so this A here, if we think about it in terms of a surface area, right, this would be the surface area of some object. This is the intensity. And yeah, we have an extra pi here. So this luminosity ends up being roughly equal to that. But it's only a close approximation because there's another extra factor of 4 here. Anyway, this is just kind of to give you some ideas about what are the regimes, nothing more. Okay. Now, we have been talking about a very classical approach to optical depth. The random walk in particular, there are different treatments of it that go in and actually factor in different processes. And so these more complex treatments, one of them is called the Rosland approximation. And then another one is the Eddington approximation. And these are used in various situations. This one in the sun, this one actually, I think also in the sun, but also in ISM cases as well. And so when you will study advanced stellar astrophysics, you will probably go into one or both of these in some detail. They're listed in section 1.8 of Rubickian Enlightenment. Since we will not really use them too much here, I'm going to kind of skip over them, and you guys can read about them at your leisure. But they're a slightly more complex treatment of what we were talking about here. Okay, I think actually that's probably good enough, right? We're at the 50-hour mark or something. So I'll leave it there. I want to talk about Einstein coefficients a little bit on the next lecture before we go into chapter 2. Are there any questions?
I have a question, but it's not related to the topics that we saw today. It's more
Okay.
related to the topics on the chapter 1. And I didn't understand very well the definition of the color temperature.
Color temperature.
Yes, well, because in the lecture, in the chapter, the authors talk about different temperatures as the brightness temperature, the color temperature, and also I forgot the other one, and also the effective temperature. And they mentioned that the color temperature was found by fitting the spectrum of some source that is an unresolved source, and you don't have exactly the distance. And as I understood, the spectrum is fitting. We not matter the amplitude, I mean the intensity, only the shape of the spectrum. But I
Right.
don't understand very well what is the why it's useful to define a color temperature.
Oh, okay, so yeah, I mean, so the brightness temperature is merely it's equivalent to a flux, and it's usually it works in the Rayleigh-Jeans regime, but then it doesn't work as you get close to the peak of the black body. The color temperature, all that is just a ratio between two bands. And what that's trying to tell you is where on the black body spectrum you are. And so if you're on the Rayleigh-Jeans portion of it, right, it's going to have something where blue is brighter. And then if you're at the top, it may be equal. And then if you're the wing, the red will be brighter. And so that's what they mean. And so it doesn't necessarily matter the total normalization, it's just the ratio of the two. And the color temperature is used often to gauge what the spectral type of a star is, for instance.
Okay.
Right? So you have the R band and the V band, and you take a color, which is just R minus V in magnitudes. And whether that's negative or positive tells you something about the color, right, of the source. And that gives you, if you assume a black body, it gives you a rough temperature estimate.
Okay, thank you.
Then the other one was the effective temperature. Yeah, and I think that's again trying to estimate where the peak of the temperature is. Okay. Other questions? Doubts? Okay, good. I'll let you guys go then. Start the homework. If you have any questions, ask me by email, or you can ask at the starter class or at the end of class on Wednesday, or you can ask in office hours on Friday. Okay. Ciao.
Okay,
Ciao.
goodbye.
Bye.
Bye.
Bye.